Hello class. So we're going to continue with our module regarding the origins of quantum theory. Now we've already went over blackbody radiation, the photoelectric effect. This topic we are going to focus on atomic spectra. Atomic spectra. So here what I want to point out is we have a gas discharge tube and it's hydrogen here. So this will be hydrogen. So when you put voltage to the lamp, what's going to happen is light is going to be emitted. It's going to pass through this slit to focus the light, and then the resulting light is going to be passed through the prism where it's going to separate the light into our visible light here, and this results in a spectrum called a line spectrum. So this is a line spectrum. So classically, scientists supposed that all visible wavelengths are carried within the light. Erase this already. So carried within the light. But they noticed that when they used these gas discharge lamps for hydrogen, helium, so these atom lamps, they had these unique emission lines within the atomic line spectra. So in 1885, a scientist by the name of Balmer discovered that hydrogen emits visible light at only specified quantized, and we learned about the word quantized earlier, values. So for example, hydrogen then will have 4 lines that appear, and we could see that in the above spectra. And so let's look up here again. You can see that there's red, blue, green. So here's our red, the blue, green, blue, violet, and violet. So 4 lines appeared and could be calculated by the following formula. 1 over lambda is equal to a constant. This is called the Rydberg constant. 1 over 2 squared minus 1 over n squared. And n is an integer, like a counting number, 1, 2, and 3, and that has to be greater than 2. So this is what Balmer theorized, and the equation is fixed at 2. Okay, so you can calculate the wavelength of those lines using this equation. Okay, so here, that is the Balmer equation. Now in general, any possible peak on a hydrogen spectrum can be described by the Rydberg equation. Okay, so that's this equation. And I didn't give you the constant before because I knew it was going to be in this section. So here's our Rydberg constant again. Here's the value. Notice it's inverse meters. And the difference between that and the one prior is Balmer sets this N1 to equal 2. So he fixed it at 2, but it can be used for other series. Now we're focusing on Balmer because this is for visible light. So fixed at 2 for visible light. But you can do it for different wavelengths as well. So over here, I have the different series. So here's the Balmer, and notice that with the Balmer series, it all will end at n equals 2. Okay, so here's the Balmer series, and there's our n equals 2. We also have the Lyman series, which is in the UV region, and you have the Paschen series. So we're not going to focus on those. I just wanted you to be aware that there's other series, but in general, you can use the Rydberg equation. So if you want to calculate a wavelength, so this is, you want to use this equation if you want to find the wavelength. So this is to solve for the wavelength, and then our units here will have to be meters. Now, another way to write the Rydberg equation is the following. So you have a change in our energy. To solve for the energy, why we do this is we want to have the unit of joules. So notice the Rydberg constant here is different. It's in joules. And this change in E, solving for that indicates the direction of energy flow. So if you get a minus value, that indicates that energy is going to be released. And if you get a positive value, that's energy absorbed. Okay, so we're going to do an example using this formula a little bit later, but I just wanted you to understand that there's a couple different formulas that we'll use.